I'm going to record a section of lecture for chapter 10 through 10.2, and this chapter is about organohalides. So the obvious question is, what do we mean by that? And these are organic compounds that contain a halogen. Our typical halogens are chlorine, bromine, and iodine, but you could have fluorine in there in some cases. And they have a lot of uses. We've talked about this a little bit in class. They can be used as dry cleaning solvents, anesthetics, insecticides, refrigerants, and other things. But they've been found that a lot of them are carcinogenic, and so the health issues have caused them to disappear from some uses as much as possible, from, say, dry cleaning, where people that were working in those dry cleaning companies were exposed to a lot of the solvent vapors, so they've tried to get them out of places like that. But they're still used in other places as solvents, for example, quite often. And they're also implicated in the freon. Some of the freon molecules cause photochemical smog problems in the upper atmosphere. And so we've tried to change which freons we use to limit the damage to the atmospheric ozone. But anyway, they are important, and there are a number of them that are common in organisms, particularly in marine organisms, because the ocean is full of halogen anions. So I have an example of such a thing from the sea snails. There's a purple color that was very popular as a royal color, and this is a picture of the royal purple called Tyrian purple. And so you've got two bromine atoms in there. In terms of nomenclature, we already know how to use halogens as part of our nomenclature of alkanes, alkenes, and alkynes. We've used halogens also as examples when we were looking at molecules that had stereocenters in them, so there were R or S configurations, and also the geometric isomers E and Z. We've talked about halogens and all of those things already. So the only thing I'm going to talk about in terms of nomenclature in this chapter are some common names that you need to know. And so this molecule's IUPAC name would be dichloromethane. Its common name is methylene chloride. And we've used the CH2 group before as in this molecule. That was called methylene cyclohexane. And so CH2 is a methylene group. So here's another way of using that in a nomenclature sense. The common names for the one carbon molecules that have three halogens on them end in form is the common name. So if it's bromine, it's bromoform. If it had been chlorines, it would be chloroform, and so forth. And the old style of nomenclature, they call this carbon tetrachloride, or carbon tet for short. And again, you could have other halogens here, but that was used a lot as a solvent, and also we use that to kill both chloroform and carbon tet were used to kill bugs and other things. Chloroform was used as an anesthetic. They've just gotten away from that. And we've used this terminology before also, vinyl chloride. That's the monomer for making polyvinyl chloride, or PVC, which we use in plastic pipe and some other places. Remember, anything that's directly attached to an alkene carbon is called a vinyl carbon. In terms of properties, the introduction of the halogen causes there to be a polar bond. So the carbon has positive character because the halogens are either more electronegative than carbon, or in the case of iodine, we talked about that a little bit, it's so much bigger than carbon that it still effectively polarizes the bond. And so for all intents and purposes, anytime you have a halogen attached to carbon, you're introducing a polar bond into the molecule where the carbon has positive character. Another interesting thing about these organohalide compounds is that they're more dense than most other organic compounds. In other words, if you have a mixture, or you put together in the same flask some, say, chloroform and ether. The ether will be on top of the chloroform because the chloroform is more dense. And you can take advantage of that sometimes with extractions using aqueous solution because they're more dense than aqueous solutions as well. So we're going to talk now about the preparation of alkyl halides, and we have a few things that we've done already, but we're going to talk about something that we have not talked about previously in a lot of depth, and that is the free radical halogenation of alkanes. And it was actually introduced in chapter 6 as an example of a free radical reaction. The reaction will only be exothermic or favorable if you use chlorine or bromine. And what happens in the reaction is you're going to do a substitution where you're substituting a hydrogen off of the alkane and putting in a halogen in its place. A lot of times you get mixtures when you do this reaction. It's not very easy to control the outcome. And so we don't do this in a lab very often. And also even the material way that you do the reaction, usually using gases and so forth, it's just not that easy to do in a lab. So we will not see people using it in, say, synthesis problems in a lab very often. But industrially, this is why these things, one reason they were so common as solvents and so forth, is because they're easy to make. In the industrial setting, it's also easy to separate all the different compounds that you get out, and pretty much all of the compounds would have some kind of use, and so if you could separate them from each other and then sell each one separately, it didn't matter that you were making mixtures. And every radical mechanism proceeds through steps. And that was one of the things we talked about in the context of chapter 6. So the initiation step is going to involve the breaking of some of the halogen molecules into halogen radicals. Now we're using chlorine as an example here, and we say that this bond breaks homolytically because each atom gets one of those bonding electrons. Now the rest of the electrons are not shown on the chlorine. Remember, chlorine has 3 unshared pairs around it, so they're still here, but the net effect is that this chlorine has an odd number of electrons on it, and so we call that a radical. And once you get a radical, then a radical will not be happy. It wants to get to an outer shell of 8, and so it wants to find something else to react with. And one thing it might run into is a molecule of an alkane that you put in there. And so we're doing methane is our first example. And this, like I said, was introduced in chapter 6, so this was the example that they showed in chapter 6. So if this electron and one of these electrons go together to make a bond, you get a molecule of HCl. And the other electron stays with the carbon, and so you make a methyl radical. Well, the methyl radical is not happy either, and it might run into some chlorine molecules and again break this bond homolytically and recreate another radical. Now this is called propagation because you have a radical on both sides of the equation. A radical begets a radical. As long as radicals are producing more radicals, it will keep going. Now what we want is to see the overall reaction, and so the way you get that is you add together these two propagation steps. And anything that's on opposite sides of the equation that's the same thing will cancel each other out. In other words, I have chlorine radicals on both sides and I have methyl radicals on both sides, so they're going to cancel each other out. So when I add these two steps together, then what I'm left with is a molecule of methane, which is now written in kind of the short version. This one was kind of emphasizing this bond. And chlorine, again, we can just condense it back to a molecule. And chloromethane. So this is the overall reaction, or the summary of what goes on in these propagation steps. And termination can occur when any two radicals run into each other, and that stops the propagation in that little area of the reaction cloud. And so if a methyl radical combines with a methyl radical, you get ethane, which is not something that we were seeing as a product in here. So this is the first example of something extra that can form. Now, if you put a chlorine radical and a methyl radical together, you just get more chloromethane, which is fine. Or you go back to chlorine if you put two chlorine radicals together. So you can kind of think about this kind of like where these reactions are occurring. You have this whole container of these molecules, and any of them that happen to start reacting is like water droplets falling on the surface of the water, and they you get these little concentric circles going out and causing this little propagation of this little energy cell. And whenever they run into each other, they stop. So this would be like two little concentric circles of water droplet energy wavelets coming out and running into each other and stopping the process. But as long as there's more radicals being created, then they just keep going. And remember that when we talk about this, that there's a whole, this represents a whole mole of chlorine molecules. So some of them are doing this, and some of them are still available to react with the carbon radical. And one of the things that we also said was that you can get these mixtures. So yeah, this methane can react with chlorine molecules, and this is the symbol for light energy, to make the chloromethane and a side product of HCl. Well, this guy could also happen to interact with a chlorine radical once the concentration of this builds up. And so if that reacts with a radical and you lose a hydrogen and then it reacts with another chlorine molecule, you get methylene chloride. And as that concentration builds up, you could make chloroform, and if that concentration builds up, you can make carbon tet. So all of that can lead to this mixture of products where you have a progression of replacing all those hydrogens one at a time with chlorines. And so industrially that's fine, but we wouldn't like to have all those things in a laboratory procedure. And of course, methane is a really simple molecule. It only has one type of hydrogen on it. I can't tell the difference between any of those hydrogens. And when we get to more complicated molecules, there are going to be other types of hydrogens, which when we talk about types of hydrogens, we're usually talking about degrees of hydrogen. And so we can complicate things as soon as we leave the very simplest idea, which is methane or ethane. So, our primary carbon to hydrogen bonds are actually less reactive. We read this less reactive than our secondary carbon hydrogen bonds, and then those in turn are less reactive than our tertiary CH bonds. And so this is kind of the order of reactivity, so 5 is the fastest. And what that implies is that as we break the CH bond, we're creating a carbon radical. We're leaving behind a carbon radical. The implication of this order of reactivity is that the tertiary carbon radical is more stable than the secondary, and in turn is more stable than the primary, and so forth. And so if we have molecules that have all those different degrees of hydrogen in there, we've got the possibility of replacing any one of those hydrogens with a halogen, but we're going to see a dominance of the more substituted higher degree hydrogens being replaced first, because that's going to be the fastest and the most exothermic reaction that these molecules can do. It might help if we go back and look at the table of bond dissociation energies. Remember that we've kind of talked about this before. If we just look at a methyl CH bond, that was worth 439, which is the strongest CH bond out of this family. This is one is primary, secondary, and tertiary. So it's easier to break this bond because it's weaker than the ones above it. So suppose that you have this molecule, and this is not a very complicated molecule. It has a hydrogen here, and you see this carbon is tertiary, and all the rest of these guys are primary, and I can't tell the difference between any of those. So I have two different degrees of hydrogen. And so the question is, if you were going to do one substitute a chlorine for one of those hydrogens, which one would be lead to the most favorable product. And it's the tertiary. We just talked about that this bond is weaker, and that's going to be, therefore, the fastest one to break, and that's going to lead to most of the product. So we're going to estimate the enthalpy for this reaction. And so we have to go back to the table and get some numbers. And the numbers that we want are for the tertiary CH bond, the chlorine-chlorine molecules bond between the two chlorines, and the tertiary carbon to chlorine bond, and the bond between the H and the chlorine for the other product. So everything has to be taken into account when you estimate enthalpy. So these are the numbers from the table that we had on the previous slide. So we add together the bonds that are being broken, and we subtract the sum of the bonds that are being made, and we get minus 129 kilojoules per mole for this particular reaction, which means it's a very favorable reaction. So let's practice writing the steps that this molecule would go through to get to this product. The initiation step, remember, is the weakest bond in here, and now you've actually got the numbers. The chlorine-chlorine bond is weaker than any of these CH bonds, so that's what's going to initiate. And so some of those will break apart, and then those radicals will react with the tertiary CH preferentially to give you the tertiary radical because it's more stable, and then that will react with other molecules of chlorine that hadn't been involved in initiation, and then you'll get the product. And again, when we cancel the same things in common on opposite sides, the chlorine radicals will cancel, the carbon radicals will cancel, and we'll be left with the summer reaction, which is the isobutane, and the chlorine molecules will give you HCl and the chlorinated product here. So that's how you get the summary. The reaction energy diagram for all of these reactions is going to look something like this. You're always going through two steps, which means there's always going to be a reaction intermediate, which I've drawn in here. For this particular reaction, it was this carbon radical. So all of them are going to have a carbon radical, and so there it is. And so the first step is the rate determining step. It's got the highest energy of activation. So here's our energy of activation. Remember, we were starting with a stable molecule and chlorine, which is fairly stable molecule. And so we have to mess up those stable molecules. So that's a large energy of activation. This radical is not particularly happy, and the chlorine-chlorine bond's fairly easy to break. So that step is a lower energy step. And so then we finally get to product, and our overall reaction is exothermic because the energy of the starting materials is higher than the energy of the products, and so we have a negative delta G. So all of them are going to look like this. They're all going to go through steps, and they're all going to have a two-step or two hills in the reaction energy diagram. So what else could we ask? You know, I mean, an obvious question is, well, we started out by saying you could not do this reaction with iodine. And so we might look at that reaction. We might compare some halogenation reactions on the same molecule. So the only thing that's going to differ is what is the halogen. And so, so we can compare the reaction energies, the enthalpy for chlorination, bromination, or iodination. So here's a little table. You notice we're always talking about breaking the CH bond here. So in the table that would be C2H5-H is the number you're going to get, and it's 420. And then the different halogens, chlorine bond is 243, bromines is 193, and iodines is only 151. So that bond is easier to break, but that doesn't tell you the whole story. So then we're looking at the new bonds that we're making, and again, that's going to be written as C2H5-X in the table. So we look up those numbers, and they change, so they're not all the same, And the weakest one is between the carbon and the iodine. And that's really a lot of the story here, is that because iodine is so big, it makes a weaker bond. So even though it was easier to break iodine from iodine, you're not gaining very much. And you're not also gaining very much in making an HI. And so the net effect is that iodination would be an endothermic reaction, not favorable. Whereas chlorination and bromination are exothermic, they are favorable. So back at the beginning we said we could only do this reaction with chlorine or bromine, and now you know why we can't make it work with iodine, because it's just not favorable. So another question that you might ask is, well, we keep talking about making substitution occur between one of the CH bonds is broken, and so the hydrogen is substituted by a halogen. So here, halogen has replaced or substituted for one of these hydrogens. So you might reasonably ask the question, do we ever break a carbon-carbon bond? So we need to write down what such a thing would look like and estimate the enthalpy for that reaction. So we'll start again with a simple molecule. We could even use the same molecule. We could use ethane. And so what we would be seeing is that if we broke this bond, the first carbon would get attached to the chlorine radical, and then that would leave behind a carbon radical, which could then react with another chlorine molecule, and you'd end up making two of these. Now, it's not always going to be quite that simple, but with this particular example, that's all you'd get. So if we're going to estimate the enthalpy for that, we have to look for the carbon-to-carbon bond. We already know what this one's value is. That's 243. And then we need to look for this value right here. And so when you go back to the table and find those, this carbon-carbon bond between the two carbons was 376. We had that number. And now we're making two of these. So that methyl carbon to chlorine bond is 351, so we multiply that times 2 because we made two of them. When you do the math, you get a minus 83, which is an exothermic reaction. So then the logical question is, well, okay, so why don't you see that? And let's compare that to this reaction up here, which is minus 107. Well, first of all, which one is more favorable? The one at minus 107 or the one at minus 83? Remember, the more negative, the more favorable. So this one has a higher enthalpy, so that one's more favorable. Something else you might consider is that this carbon-carbon bond, that's a sigma bond, and that pair of electrons in that bond is kind of buried in the middle of this whole molecule. And so it's harder or less likely for the chlorine radical to go past all those hydrogens to get down in there to get to that carbon-carbon bond. So just kind of on a gut feel kind of way of looking at it, it's just easier for the chlorine radical to snag a hydrogen off the edges than to get down into the middle of the molecule to break that carbon-carbon bond. And ultimately, it's not as favorable to do so anyway. Here's another kind of question you might have. Which of these molecules could only give you a single product? And the kind of product we're talking about is, I call it monohalogenation, which means one hydrogen is substituted with one halogen. Okay? So you need to look at these molecules, and the way to answer this question is really look for symmetry, look to see how many different degrees of carbons and hydrogens you have, and that kind of thinking is what you need to do. So if you start out with molecule A, all of these CH bonds, all of these carbons and all the CH bonds are secondary. And if you think about cyclohexane, you know, you've got axial and equatorial hydrogens, but remember the chair can flip. You can't really tell the difference between any of these CH bonds. So if we were going to replace any one of those hydrogens with a halogen, I wouldn't be able to tell which one had originally been where on that molecule. So compound A would give me a single product. All right, so let's consider B. Well, I've got a tertiary carbon, a secondary carbon, and I have 3 primary carbons. So right away you can see that I've got several opportunities. Now the tertiary one would be the most favorable in enthalpy calculation, remember we talked about that, the second most favorable in terms of enthalpy would be to do a secondary position hydrogen. And then you've got these primaries, but these two are identical to each other, but this one is different. In other words, if I replace one of these hydrogen with a halogen, I'm not going to get the same product as if I replace one or the other of these with a halogen. So in other words, I can get 1, 2, 3, 4 different products from compound B. And the most favorable is going to be here, and then this one, and then the primary ones are about the same in terms of the calculation. How about for this molecule? Well, you notice that there's no hydrogens anywhere in here, so the only place I have hydrogens to replace or substitute for are out here on these methyls. And again, I can't tell the difference between any of these guys. So if I do any one of these CH bonds, I'm only going to get a single product. So C would also work. Well, how about this guy? We'll have a primary and a secondary and another primary. Well, as soon as you have 2 different degrees, then you could get 2 different products. But also, this primary is next to a secondary. This primary is next to, well, it's a secondary, but it's a triple bond. That's different than this one. So I could get 3 different products out of this one. So the correct answer to this question was A, and C would give you only a single product. Alright, so that's the end of the lecture material through section 10.2.